I really appreciate this opportunity to give a lecture to a new audience. And the title of the project that I'm working on and that I will present today is the arbitrage portfolios or C-based characteristic-based return. So this is a joint work with Bob Korajczyk at Northwestern University and Andreas Neuhierl at WashU. So in this paper, what we propose is basically a new method to extract an arbitrage opportunity from a large cross-section through various form signals. So that is our objective. Okay, I'll start with an overview. The key idea of this project is the separation of alpha and beta. So as a parable in the Gospel of Matthew, chapter 25, there's a prophecy that in the last judgment day, the Son of Man will come to the earth and separate sheep from the goats. And this is a painting by Angelico, which describes the last judgment day. And what if we can separate alphas from betas in the returns? Then we can do an amazing thing, okay? Let's assume that we know the alpha and beta, then let's hold a portfolio with the portfolio weight of n by 1 vector, which is proportional to the size of the mispricing level, alpha. Then you will get the portfolio returns, which is this. Then the excess return can be decomposed into mispricing component and systematic risk component and the diversifiable risk component. Then let's see what you get. What you get will be this part, which I call as an arbitrage portfolio. And this part and this part will disappear because you are not going to have any exposure to the systematic risk, and all of the residual component will be diversified away. So if we know alpha and beta, then that is great. But the problem is we do not know either alpha or beta. So what we propose in this paper is let's use form level characteristics which are known to be related to the cross-section of the returns, such as size and book to market. So let's see what we can do. Okay, and the literature has identified hundreds of return predictors which are known to be related to the cross-section of the returns. But the problem is we do not know why such predictors are related to the cross-section returns. Is it because of the exposure to the systematic factor, or is it because of the mispricing, or both? The literature is not well developed to answer this question. But the most prevalent approach in addressing this question is a portfolio construction by double search on the characteristic and associated effective beta, which is proposed by Daniel and Titman in 1997. But I can show that their method has some significant flaw through the simulation exercise. So let's assume a very simple economy where CAPM holds. Return just follows one factor model, and there is no alpha in this economy. But there is a characteristic which is linearly related to the beta, the exposure to the systematic factor. And then let's sort individual stocks in this economy, first on characteristic, and then on estimated beta. Estimated beta using the past data. Then the numbers in this table are returns of those portfolios. And what you can observe is there's a large return spread on this dimension. Characteristic dimension, you can observe a large difference in return, but you do not observe that much return difference on this dimension. Okay, we know why this is the case, because characteristic is just proxying the beta better than the past beta. But what if you do not know the structure of this economy and just observe this table first? Then it is highly likely that you will conclude that this characteristic is related to the alpha, and the beta does not provide that much information in explaining the cross-section of this economy. But that is not true. The reason that we observe the large difference in the return in the characteristic dimension is characteristic is a better signal of beta than the past beta. But if we use our method, I did not explain our method yet, but if we use our method to this economy, then we are not fooled. We can identify that this characteristic has a minimal, it's a virtually zero relation to the alpha. And that is what we're supposed to conclude, because in this economy, there is no alpha. Okay, so let me explain the goals of this project. So we want to propose a novel method which uses a large number of individual stocks as well as can handle many characteristics. But the main purpose of this project is we want to identify the relation between characteristics and alpha, as well as the relation between characteristics and the beta. And as will be shown, we will accommodate both a general factor structure, but also we will allow the time-varying cross-sectional relation between characteristics and the alpha as well as beta. Because if investors can learn about predictors and the relation between characteristics and alpha and can exploit those information in generating, in optimizing their portfolio, then those information should disappear. And we have empirical evidence of that in a recent paper. And also we will provide some simulation evidence that our method works well. And then we will apply our estimator to real data, the US stock returns. Okay, now I will skip the related literature. And this is a preview of our empirical result. And we show that our procedure works well in disentangling an alpha and beta, at least in a simulated economy. That's why I present this. And also we find that in the US equities, some characteristics are highly related to beta and some characteristics are also highly related to mispricing. And also we will propose a new portfolio which exploit the relation between characteristic and mispricing. Then this portfolio performs very well. The annual Sharpe ratio are way higher than 1.5. And also the alphas against most common factor models are 2% per month. And we find that the returns tend to decline, but only marginally. And also the results are quite robust to excluding small funds. Okay, so let's go into the theory. The first, I will construct some economy. Okay, so in this, I'll construct an economy where the return follows some K-factor model. Returns can be decomposed into alpha and the systematic factor component and the residual component. And for the sake of notational convenience, I will use the matrix notation of the R, alpha, beta, F, and E. Okay. So basically, what I assume that in this economy, the returns are generated by K-factor model. But note that what we observe is only the return, excess return. But we do not observe alpha, no beta, no factor, no residual. And I also want to highlight that we put alpha explicitly so that if there is some information about the mispricing, then we can exploit it. So many papers which assume some equilibrium in academics, then they implicitly assume the alpha to be 0. Okay. As I said before at the beginning, it will be great if we know alpha and beta, but we want to consider a situation that there is a large cross-section of the asset. And also, if there's a large cross-section of asset, then individual stock returns tend to be quite short. So we need to set the time dimension to be quite short. And also the information about the relation between characteristic and the alpha and beta can change. So we need to set time to be fixed. Under this situation, it is impossible to learn about the alpha and beta accurately enough. So what we do is we put some structure on the alpha and beta. We assume that the alpha is some function of the fund characteristic plus some components which are not explained by characteristic, and the beta is also some function of characteristic plus unexplained by characteristic. So we call this the G beta as a factor loading function, which relates characteristics into the betas. And we call this G alpha as mispricing function, which maps characteristics into into alphas. And also we need to put some formal assumptions about G alpha and the G beta, mispricing function and the factor loading function. And the first assumption is that the squared average of the G alpha is will converge some value, which is not restrictive at all. But what I want to highlight is we allow the possibility that the characteristic may have some information about the alpha. But this is not going well with the conventional assumption of the APT, because the APT implies that the squared average of the alpha approaches to zero. Then this will imply that squared average of the mispricing function also be zero. But in this paper, we do not impose this. We just ask empirical data whether it holds or not. So we consider this as an empirical question. Whether this object converges to zero or not is an empirical question. And the second assumption is mispricing function and the factor loading function is cross-sectionally orthogonal. But this assumption is in fact without loss of generality, because if there is any correlation, we can always project the mispricing function, the correlated part, onto the factor loading function, and we can reconstruct the mispricing function as a residual. But in terms of economics, we can interpret this assumption as we want to give a maximum power to the systematic factors to explain the cross-section. Okay. So far, I defined economy. So now we are ready to develop a new methodology.
Professor Kim, I had a question.
Yeah.
Can you please go back 2 slides? Yeah.
This one?
Yeah. I didn't exactly understand the implication of G alpha star and G alpha, basically the squared average of G alpha converging to delta as compared to converging to zero. What is the implication? Is the implication that if you do this on an empirical set of data, if it doesn't converge to zero and converges to some delta, that means that the underlying time series has alpha in it?
No, this is not a time series alpha. Okay, so let me go back to the return generating process. So this alpha is n by 1 vector. So this alpha is a cross-section of mispricing.
Right, okay.
Okay. And what I want to say is we do not impose that this object converges to zero. Okay, this is always positive. Okay. This is always non-negative at least, right? It's a squared average. But if we believe the APT, then we should set this to be converging to zero, but we do not impose that. We are asking whether this converge to 0 or not as an empirical question. Did I answer your question?
Sort of. Just clarify one thing for me, please. If alpha is assumed to be 1 by n in size, is G alpha x also 1 by n in size?
Yeah, that's right.
Okay, so this is essentially the matrix, a 1 by n matrix into an n by 1 matrix, which then makes the dot product divided by basically the number of elements.
That's right.
Got it. Okay, that clarifies it. I didn't know the size of G alpha x. And
Okay.
what was the size of G beta x?
G beta is has the same size of the beta B,
Right.
which is n by k, n by the number of systematic vector.
Got it. Okay, thank you.
Okay, so I'll move on. So far we construct an economy, so we are ready to develop a new estimator. So first I will explain how the estimation procedure is going at a high level. The estimation procedure is in 3 steps. In the first step, we will learn about the vector loading function in step 1. And in the step 2, we will learn about the mispricing function. And step 3, we will construct an arbitrage portfolio. Okay, I will explain each of these steps in details. So the first step is we want to learn about vector loading function. Okay. So I said the returns can be decomposed into mispricing component and systematic risk component and the residual. But in this step, we want to learn about vector loading function. So we do not need this. We do not need this. So what we do is we multiply JT, which has an effect of the demeaning. So for example, if I multiply 2, 3, 1 vector with a J3, then what we get is a demeaned version of 2, 3, 1 is 0, 1, and minus 1. Just 1. Do you see me?
It's all good.
Yeah, so there was some problem on my monitor. Sorry. And so we multiply JT, then what we get is we can drop this alpha. So the demeaned return will become beta times demeaned factor plus demeaned residual. So we like that alpha is dropped out, and these demeaned returns are only related to the systematic risk, but still, because we have a short time series, we cannot estimate B itself. So we need to move further. So in the next step, what we do is we multiply this demeaned return on the characteristic space by multiplying this projection matrix. So this owl head is a demeaned and projected returns. So if we project this demeaned return, then the vector loading function component will survive because vector loading function is already a function of the characteristic. But this projection times this residual component will disappear because this residual is nothing related to the characteristic. And also this residual component will be diversified away. So intuitively, this demeaned projected return will be very close to vector loading function times demeaned vector. And we can formally show that if we apply the PCA to this, the product of the demeaned projected return, then it will become very similar to this. So if after we identify the eigenvector of this product, then we can show that the eigenvector actually converges to this vector loading function. So we are done with the step 1. We know how to identify the vector loading function. Then let's move to step 2. In the step 2, we want to learn about mispricing function. So for this purpose, we use average return. So average return will contain the information of the alpha and beta of it. And if we plug in the expression of the alpha and beta with the mispricing function and vector loading function, then we get this. So you can see that we cannot use the same strategy in the step 1 because this one contains the information about this mispricing function and the vector loading function. So what we do is we use some trick that we regress the average return on the characteristic space, but we impose additional condition that the projection is supposed to be orthogonal to the vector loading function that we identified in the step 1. So if we do this constrained regression, it turns out that the projection will converge it to the mispricing function. Okay, so now we know how to identify the mispricing function. Okay, the last step is a construction on arbitrage portfolio. So let's assume that we know the mispricing function exactly, although we do not know. Then if we know this, then let's see what happens. If we know this and hold this as your portfolio, then your portfolio return will become, will be decomposed into these many components. And it turns out that this component will go to 0 because this part is a cross-sectional orthogonality characteristic, and the cross-sectional orthogonality between mispricing function and vector loading function will guarantee that this will go to 0. And this component will also cross-sectional orthogonality characteristic, so this will go 0. And this part will diversify away because this part is a residual. So if we can construct this portfolio, then this portfolio will deliver delta profit. Okay, remember this is an excess return, so you do not pay any price today, but tomorrow you will get delta, which is positive, it's potentially positive. But we do not have that. But nicely, if we construct instead of using the true G alpha, if we use the G alpha head, which we get from the step 2, then it turns out that the nice property can be preserved. So if we just construct this portfolio, then you will get an arbitrage profit, if there is an arbitrage. Okay, then I'll go to a simulation evidence. So first I will explain that how we apply our method in an out-of-sample manner. So remember that the theory does not require large T. So construct a fixed horizon of time. And for the first, using the first part of the data, we construct some arbitrage portfolio. Then using this constructed portfolio, we hold some portfolio for the remaining period. And for the simulation, as well as in our empirical exercise, we use a 12-month data to construct an arbitrage portfolio. And for the next month, we hold that portfolio. So I will skip the calibration part. So I will skip the details, but I want to explain that we calibrate the individual stock returns to fit this 4S pricing model, CAPM, Farmer Branch 3-factor model, and 4-factor model by Luzin, and also the Farmer Branch 5-factor model. And we simulate the returns based on this formula, and alpha is calibrated such that the squared alpha converges to 1. So if there is an arbitrage profit, this part, the squared average of this part will be delta. And also we consider 3 different levels of delta of 0, 5, and 10 basis point. And as I explained before, we construct the arbitrage portfolio using the first 12-month data, and we hold the portfolio for the following month. And we repeat this exercise 10,000 times. We consider many different versions, but let's look at the baseline case. And this is the distribution of the arbitrage portfolio return for the CAPM and final furnished 3-factor model, 4-factor model, and 5-factor model. The results are quite similar, so I just focus on this. And the first two is the case when delta is 0, and next two is delta is 5, and the last two is delta is 10. As you can see, the average level is on the target delta of 0, 5, 10. And also you can see that as the size of the cross-section increases and the accuracy of the portfolio profit also increases. So this length means the 95% interval. And also we consider many different versions where our assumptions are not exactly matched, but we find that the results are quite robust. So for example, if we extract too many factors, for example, for the CAPM, the true number over the systematic factor is 1, but we extract 2. But still, the results doesn't change that much. Okay, so finally, let's go to the empirical result. So in terms of data, we use CRISP and computed data to create the 61 characteristics. And the sample period is from 1965 to 2018. And this is a list of characteristics that we used, such as market cap and book to market and profitability, investment beta, and the idiosyncratic volatility, and etc. This is 61 characteristics. So I cannot read all of them. Okay, and also there are some hyperparameters that we can choose. So we need to make some parametric assumptions that the G alpha and G beta is linear, but we also consider non-linear case in the robustness section of the paper. And also we use, as I explained before, again, we use 12-month moving window for the construction of the arbitrage portfolio. And in the following 1 month, we hold that portfolio. And also the G beta, as for the G beta estimation, G beta, the dimension of G beta is the factor loading function is m by k. So we need to pick what k we will use. So we do not need to take a stance on what is the right number of the factor of the systematic factor. So we just consider different number of estimated factors, many different versions. And also we scale the estimation period volatility of the arbitrage portfolio over the 12 months of the estimation window to 20% annual. And this is the performance summary statistics of our arbitrage portfolio. And the number of eigenvectors means that how many factor loadings did we extract from the PCA? From 1 to 11, because it is the mean data of the 12-month returns. So the maximum number of eigenvectors we can extract is 11. And if we extract 11, then there's nothing left. So we cannot compute the misprice function. So practically the maximum number is 10. So we consider all the different possible versions. And this is the annual Sharpe ratio of the arbitrage portfolios. And you can see that it tends to increase and it's quite stable at between 3 and 8. And also I want to highlight that. So this is the maximum drawdown of our arbitrage portfolio, and I can see that the size of maximum drawdown is much smaller than other popular factors. For example, the maximum drawdown of the market is 56%, size is 55%, and etc. Okay, so the high Sharpe ratio is good, but if this high Sharpe ratio can be constructed with the existing factor, then we are not making a big contribution. So we regress our arbitrage portfolio returns against many popular asset pricing model, and we find that the intercept is quite strong. So for example, even when we use only one eigenvector, the CAPM, the alpha over our arbitrage portfolio against CAPM is 1.64% per month. But if we use 6 eigenvectors, then the size of the alpha is substantially increased. For example, we get a 2.5% alpha percent per month alpha against CAPM. And this is the summary plot of the alpha, of the monthly alpha. And so the vertical line vertical axis represent the size of the alpha, and the horizontal axis represent the number of eigenvectors, and its different line represent the different vector model to compute the alpha. And all of these numbers are positive and statistically significant with a 1% significance level. It tends to increase against at least up to 6, but it's decreasing if it goes over 8, 9, 10, probably due to overfitting. And we also ask some economic questions. Okay, what we show is the average performance of our arbitrage portfolio, but what if the performance has been declining over time? So we regress our arbitrage portfolio returns on the intercept and some power function, but we find that there is some trend that the size of the average return of our arbitrage portfolios tend to decrease, but it's not statistically significant. So the result is quite robust. And also we examine whether our portfolio performance is depending on the state of the economy. Okay, so this black line represents the low price of our arbitrage portfolio, and this red line represents the low price if you put your money into the market. And this gray shaded area represents the MBA recession dummy. And so whenever there's a recession, you can see that there's a market drop down. As you can see, it's almost monotonically increasing over time, our arbitrage portfolio. So we regress our arbitrage portfolio returns on an intercept, constant, and the MBL dummy. And in fact, our arbitrage portfolio return performs better in the recession period, but it's not statistically significant. Okay, so let me conclude. So in this paper, we propose a new methodology to estimate the mispricing and the risk in the information of the characteristics. And we find that the role of characteristics is changing substantially over time. And we find that some characteristics are related to vector loading and some characteristics are related to mispricing. And we also propose a novel arbitrage strategy with economically and statistically large alpha. So for next project, we want to explore if we use a machine learning technique for estimating the mispricing function or if it's the loading function, then the performance will be improved or not. And also we are starting a new project in the international market, so that we can identify the mispricing across country using a similar framework. Okay, thank you very much.